So, hello everyone. Well, we have the pleasure today to have Kento Osuga from the University of Warsaw. He will talk about super topological recursion. And it is a pleasure to welcome you. So, Kento, please, you can start presenting.
Okay, thank you very much. And first of all, I'd like to thank the organizers for giving me, sorry, but how can I remove this? Maybe I have to move this one down. And it's gonna disappear, maybe. Sorry. How can I remove this, the top tab?
This what?
This top tab. Oh no. Sorry, one sec. No, I was wondering how I can remove this tab.
I think you are in full screen.
You see something here, right? So, sorry, can I? Sorry, I'm sorry for all the audience, but let me now try to share the screen again. I think it's gonna work.
So, excuse me, can every participant turn their microphone off, please?
All right, good. So it's gone now. All right. Okay. So again, I'd like to thank the organizers for inviting me to speak here, and it's my great pleasure to contribute to this great seminar series of ReNewQuantum. And today I'd like to talk about my recent progress about super topological recursion. And these three are the main references, and in particular, the second one is probably one of the most important one out of these three. And when I was making slides, I just realized every year in July, I had some papers about super topological recursion. So hopefully, with or without collaborators, I'm going to have a new paper about super topological recursion in next year, July. All right, so let me move on to introduction. And I think many of the participants in this seminar knows why topological recursion is interesting. But let me still emphasize why it's a very nice object to study. So the topological recursion started from the study of matrix models. And in particular, it's a technique to solve loop equations of matrix models, in particular for correlation function. But it turns out that the topological recursion has its own life, and it can be applied to many branches in mathematics and physics. And these are just one of few applications that we can think of, but there are many others too. So, but then at the same time, you may ask, okay, why the topological recursion is so nice? Or in other words, you might wonder, maybe there's some fundamental structure underlying the topological recursion. And this is how I view the story of topological recursion. So topological recursion, if you know the formula, which I omit to write down here, it's essentially a Pan's decomposition formula. And then the gluing rule between the edges are specified by picking up residues. And now you may ask, where is it coming from? And it turns out the topological recursion is one way of solving a fundamental system of equations, so-called abstract loop equation. So from this abstract point of view, topological recursion is a method to solve this fundamental system of equations. And recently, by Conservich and Sobelman, there's another proposal to solve abstract loop equations, in particular by utilizing the power of Virasoro algebra, or more generally, vertex operator algebra. And this new way of solving abstract loop equations, it's known as Airy structures. And today, the question I'd like to address is, can we extend this story with supersymmetry? All right, so, okay, but before going to that, so today I'd like to start with this super structure part, which many of you might be less familiar compared to topological recursion, but it's because we have a guidance about this Virasoro constraints. And super Virasoro constraints, it's a very established notion. So we want to take that as a guidance, and then hopefully we go back and finally find super topological recursion. That's the path I'd like to take today. Okay, so because of the structure of my slides, I couldn't fit all of these good references into each piece of the slide. So first, I want to show you all these important results for my work. And of course, there are many other great papers about topological recursion too. Okay, so now I'm going to move on to super-array structures. And then, okay, this slide and the next slide will be a little bit technical, but I hope this gives you an impression what super-array structures are, and hopefully you gain some feeling what super-array structures are. So super structures, you have to start with a vector space, and throughout my talk, I will highlight fermionic vector or fermionic dependence with red color. So whenever you see something in red, they're fermionic. And if it's in black, they're bosonic. And your vector space is, in the ordinal sense, it's Z2 graded. So bosonic vector space or fermionic vector space. And for some technical reason, I want to split the vector space into like some vector space plus additional one-dimensional fermionic vector space.
Et je peux mettre aussi mon modérateur. Donc, un modérateur peut faire des autres modérateurs.
Bertrand?
Oui. Oui, peut-être. Je ne sais pas.
Oui, il me laisse faire.
So is that a question? Or can I go on, maybe?
People should mute. This is just a background conversation.
Okay, so I guess I can just go on. All right, so yeah, so the vector space is graded by either bosonic or fermionic. And now I'd like to introduce coordinates for each vector space. So X is the vectors coordinates for this bosonic vector space. And thetas are fermionic coordinates for this fermionic vector space. And this I indices, even though it's very small, I intentionally put I from 1 to the dimension of each vector space. But this indices never becomes 0. And it's exactly because I'd like to keep 0 for specifically coordinate of this fermionic extra vector space. And you will see towards the end why I'm treating this extra vector space as a special element compared to any other fermionic vector space. All right, and then now I introduce a grading about these coordinates, and this is nothing deep, but it's just convenient for us to count some degrees in terms of differential operators that you will see in the future. So I define degrees of each coordinates, no matter if they are fermionic or bosonic, their degrees are just 1. And now I introduce formal parameter h bar, whose degree to be 2. And based on these coordinates and formal parameter, I would like to just define algebra of differential operators. And these differential operators, in particular, this one, h bar d by dxi, this as a pair has degree 1. So any differential operators living in this definition has degree 0 or higher, but it never has negative degree. And that's why I want to have this coupled derivative. All right, so now let me give you the definition of a super structure. Super structure is purely just a set of differential operators satisfying the following condition. So for bosonic differential operators, degree 1 term has to be just the derivative. You do not have linear dependence in x's, plus any degree 2 or higher terms. Similarly, we impose the same condition, pretty much the same condition for fermionic differential operators. The degree 1 term is just h bar d by theta I plus some higher degree terms. And then depending on their parity, whenever you take commutator or anti-commutator, there must exist some differential operator living in this algebra of differential operators satisfying this condition. In particular, if f, I, j, k, if they are constant, these differential operators generate a least super algebra, but we just soften that condition such that it can be some differential operator. All right, so then now let me give you a remark, even though it's a little technical, but this is very important. So we do not require the existence of fermionic differential operator starting with h bar d by d theta 0. So theta 0 appears only in this higher degree term, but never in degree 1 term. And so naively, number of variables you have is xi's, theta i's, and theta 0 is number of differential operators, li's, these guys, plus 1, exactly because of missing factor of this differential operator. And for this reason, I call the theta 0 the extra variable. And this is describing this extra vectors. Okay, so this is very technical definition. And then if you're not familiar with area structures, you may wonder, why do we think about such set of differential operators? What is it good for? And then this is the answer why such set of differential operators could be interesting for you. So given a superstructure, given a set of differential operators with specific conditions, there exists a unique power series of x's, thetas, and theta 0, and also h bar formal parameter for satisfying the following conditions. S1, so the first condition has to be even or bosonic. And the second condition is it doesn't have degree 2 or less. This is just a technical condition that we need. But the third condition is important. The third condition means that, so if you take exponent of this free energy or power series, this guy is annihilated by all the differential operators you have in your superstructure. Okay, so now let me make it a little more explicit what this theorem is saying. So by assumption, having power series means that you can just have this expansion with some coefficients, FGN/n. And then this coefficient has to be complex number. It's just a definition. Now, the condition S1 and S2 means that, for example, this free energy can have only even number of thetas. In other words, this FGN/2n plus 1, for all coefficients, it has to be 0. And S2 means this degree 1 term or degree 2 coefficients for degree 1 or degree 2 terms should also be 0. And F3, this is very important. F3, again, it gives a set of recursive equations for each coefficient. So the reason why superstructure is interesting is exactly because of this recursive structure. And if you do not import such some maybe somewhat ad hoc condition on the differential operators, you may lose either uniqueness or existence. All right, so if you want to have some feeling what kind of recursion you can get from area structures, now I'll give you one simple example. So for brevity, let's set the fermionic definition to be 0 so that it just boils down to bosonic area structures. And in this case, I further constrain that all the differential operators are up to degree 2. In this case, it turns out that your differential operators can be characterized by 4 types of coefficients, A, B, C, and D, and they're all complex numbers. And for example, this one, you have 2 x's, so degree 2. You have h bar dx, and you have x as well, so this is also degree 2, and similarly, C and D term as well. So then now, suppose you plug in, you compute this equation, differential equations, and look at order by order in h bar and also x's, and you find that F03, the first non-trivial coefficient of your free energy, is precisely given by Aijk here in the differential operator. And similarly, F11 is given by this D term. And for any other Fgn plus 1, it's given by this recursion. Is it actually recursion? And the answer is yes. So the right-hand side of this equation, if you look at this Fgn or Fg, everything here, this always, if you compute the Euler characteristic of this Fgn, it's always smaller than the Euler characteristic of the left-hand side. So it's recursive. And more importantly, if you think of this formula in a pictorial manner, and the right-hand side can be thought of as a trivalent decomposition. And if you know the formula of topological recursion, you might find these 2 terms very similar to the topological recursion.
Hi, Kento.
Yeah.
So there is a question in the audience.
Okay. Sorry. Yeah, in the chat.
Can you see it or should I read it?
No. Okay. So does the vanishing of correspond to the fact that there always have to be an even number of among functions for? Yes, that's okay. This is actually a very good question. So in this formalism, so the question I think now everyone is seeing in this screen, but so the answer is yes in this assumption. Then you can actually generalize the definition that I gave here. But for now, I'd like to stick to this definition, and because it has nice relation to the topological recursion, the super topological recursion. But so that's my answer. So yes, you could generalize it, but for now we stick to this definition. I hope that answers to the question. All right, so then now, if there's any other questions. Okay, so if you think higher degree,
maybe I can I can also ask a question then, Kento. So
yes,
I guess Vivek's question was in some sense assuming that if you take a super Riemann surface, that there is a formulation of topological recursion on the in terms of super Riemann surfaces, and that you get a useful, topological recursion this way. Is there a reformulation of what you're talking about here in terms of super Riemann surfaces?
Oh yes, oh yeah, I'm definitely going to explain in this section super topological recursion.
Okay, super.
Yeah.
Thank you.
All right, yeah, sorry, maybe I should mention that. So this is one side of the story of the super topological recursion, the more like algebraic side. And later on, I'm going to talk about more like a geometric side. And then I will see the comparison. Good? All right, so, and then, yeah, just as a comment, if you think higher order area structures, and it's not going to be trivalent graph decomposition anymore, but it's going to be multivalent graph decomposition. All right, so now let's turn on fermionic dependence. So when you turn on the dimension of fermionic dependence, your bosonic vector can have your bosonic differential operators can have even number of fermionic dependencies as well. So even if you stick to quadratic superstructure, you have to add, in addition to A, B, C, D, you have to add E, F, G, which controls the product of fermionic dependence. And similarly, you now have to prepare fermionic differential operators. And you can easily actually count that there will be 4 more parameters, let's say H, I, J, and K. So now, if you compute these differential equations and look at coefficients order by order in H bar and X and thetas, you find a recursion, but the recursion is not just controlled by A, B, C, D, but it's controlled by A, B, C, D, E, F, G, I, J, and K. The 11 parameters, and this is a lot. And hopefully you forgive me not writing down all the recursion, but if you're interested, you can move your hands and try to derive the recursion. But at least philosophically, everything goes very well. So if you stick to quadratic area structure, it gives a trivalent graph decomposition formula with fermionic edges. And you just have to be careful about the signs and also the treatment for the extra variable. But philosophically, like conceptually, it just goes very well. All right, so far I just gave you a nice formalism that gives some recursion. But can we find some interesting superstructures? This is more like important questions. And do we have any guidance to find interesting superstructures? All right, so now I move on to interesting part of superstructures, not the technical part. So we actually have a very nice guidance from the relation between the topological recursion and W algebra. So it turns out area structures related to topological recursion of ramification order R can be constructed by twisted modules of WGL algebra. And recently, it turns out you can also construct area structure related to topological recursion, so-called without branch covers. And this has relation, so area structures can be constructed in terms of untwisted module of W algebra. And today I'm going to focus on the supersymmetric generalization of when R is 2. So it's just a simple ramification, and so the W algebra just reduces down to Virasoro algebra. And it turns out, so now we take this guidance. You want to construct super structures from modules of super Virasoro algebra, which is the supersymmetric generalization of GL2. And it turns out there are 4 classes, not just 2, right? Like ramified or not ramified. There are actually 4 classes of super structures that you can construct. And this is just a table. So somehow bookmark appears again. But this is a table for the recursion. So you can construct 4 different classes of module or 4 different classes of array structures from different way of twisting. And we actually know at least one example in physics for 3 of the modules, but one of the module we are missing application. But I want to emphasize that the recursion exists. You can actually find the superstructures, you can find a recursive equation, but we just don't know any application of one of the twisted modules. And today, I'd like to focus.
Sorry, Kento. There is again another question by Vivek.
Oh, that's probably why this showed up. What you said about arrow? Oh, okay. Yeah. So, okay. So this arrow is actually, I'm not saying in a very strict sense, but what I'm saying is, okay. Sorry. Yeah. Okay. I understand that question, but yeah, I should have been careful. So yes, the arrow actually basically. So it, given if you think about topological recursion of order, ramification order, say R, and there's a one-to-one correspondence between some module and also actually highest weight vector of the twisted modules of W algebra. And so you can actually find a one-to-one correspondence. That's what I mean by this arrow. I'm not saying they're exactly the same, or I'm not saying they're equivalent in the sense of category. And I think you will actually see example with supersymmetry as well. And then you will hopefully get some feeling what I'm saying. Okay, so yeah, hopefully, actually in the next slide or the slide after, you will see a specific example, and hopefully that explains what I'm saying. Okay, so then today I'd like to focus on the row twisted module because it's a natural generalization of topological recursion of simple ramification. And I will justify towards the end why this is a natural one compared to any other 3. So, okay, so now the question, what is a row twisted module? Now, okay, so remember that for super structures, you had a finite dimensional vector space. I want to just extend to infinite dimensional case. So you have infinite many bosonic variables and you have infinite many fermionic variables. But I still have this extra variable. And you will see in the next actually slide why this becomes important, at least intuitively. So it's a little ad hoc, but let me just tell you this set of differential operators. So these J's, they actually generate the Heisenberg algebra. So it's a free boson algebra in CFT. And gammas, they're fermionic generators, and they indeed generate the Clifford algebra. And L's, you can think of them as modes for Virasoro operators, and G's are superconformal operators. And then, okay, I'll justify some details later, but this set J, gamma, L, and G, they generate a slight extension of the n=1 super Virasoro algebra in the Nevill-Schwarz set. All right, so now let me give you a few comments about this representation of Virasoro operators. So first of all, these are fine. You know, it's a degree 1 term. And remember that the definition of superstructures, it requires a specific form of degree 1 term, like in this form. But these L's and G's, they're quadratic. You have 2 J's and you have 1 H bar, which is degree 2 again, and 2 gammas. And this one also you have J times gamma. So they're homogeneous of degree 2. It doesn't have degree 1 term. So that's at least one problem at the moment. And another point, okay, this is more like not the problem, but more like a justification. So the zero mode, it always appears as a pair in this pair. In particular, so this one, this is a theta 0, and H bar D by D theta 0. Sorry, I have a reservation. All right, sorry. So this derivative always appears a pair, and you can never split them into 2 pieces. But this doesn't give us a problem at all because we treat theta 0 as the extra variable, and we do not require degree 1 condition for this theta 0. All right, so having that being said, okay, now the question, how can we turn this set of differential operators into the form of super structures. These operators look pretty nice, but not yet, not exactly super structure. So how can we bring this to the form of super structure? And this is the answer. So it turns out, so now you have 3 ways to choose parameters, tau, phi, and psi. And as long as they satisfy some technical condition that we can forget, now let's define this operator, exponent of this here. Now we take a conjugate of the differential operators in the previous slide by this phi. And now it's, okay, let's do some counting problem. You have 1 over h bar here, and you have j here and product of j. So this term is degree 0. And this one also degree 0. But this one, it's 1 over h bar, but you have only 1 j. So this one gives degree -1. So whenever this acts on some differential operators, it reduces the degree by 1 for some term. And then it turns out that if you take this conjugation for any choice of parameters, and then this set of differential operators defines a superstructure. And thanks to the theorem of superstructure, there exists a unique free energy or unique power series. And this is, you might find it interesting because this is some sort of power series associated to the super-Virasoro algebra. Okay, and then now, sorry, I have a reservation. Yeah, but I'm giving online. Okay, sorry for the okay, what did I say? Oh, sorry. Okay, so now, okay, as a summary of this section, so you can think of superstructure as a machine that takes tau, phi, and psi, this choice of parameters, like as much as you like, as long as it satisfies this condition, and it spits out FGN/2n. All right, so that's basically a summary of super Airy structures, and hopefully this answers to the previous question. So the point is, we can construct some canonical set of differential operators. What we have to do is you basically have to take this conjugate by this operator, and this gives basically the information about the spectral curve that I'm going to mention now. All right, so I think this is a good point of asking questions if there's any. So this is basically one side of the proposed recursion. So are there any questions? All right, so I guess I can move on. So now, so this was, okay, so this is a good picture. So far I described only about algebraic side of the story of super topological recursion. And here it was nice because we had a guidance. We had a super Virasoro constraint, and it was not trivial, but there was a nice guidance to construct what super structures could be, what should be, and what kind of Airy structure we expect from super Virasoro algebra. Now the tricky part is the construction of abstract super loop equations, which are supposed to be the fundamental structure underlying this story, and from which can we geometrically, by utilizing, as Jürgen asked questions, by utilizing the geometry of superima surface, and can we construct some nice recursion, the dual part, geometric part of this. All right, so yeah, okay, so as I said, we had a guidance, but it doesn't seem clear for the other path. So are there any constructive approach? And then now we have to come back to the origin of the topological recursion. It emerged from the study of Hermitian matrix models. So a natural speculation is, can we think about supersymmetric analog of Hermitian matrix models? And such model exists, and they are called super eigenvalue models in the both Nevius-Waltz and Ramon sector. All right, so even though it's a little tedious, you can ask the following questions. Do they admit loop equations? And if so, can you find a spectral curve by looking at the leading order? And the answer is both yes to this model. And now we have a spectral curve for each model. And you can ask, what is the core structures for correlation functions? And you can investigate that by utilizing the super loop equation. All right, but now so this is fine. You have a specific model, you can compute something, and you can try to find the recursion. That's not so difficult. And a non-trivial part of this work is to find universal structure in their loop equation, regardless of the sector. And this part was a little tricky. And I'm not going to tell you any detailed story about this, but I just want to share some conceptual part, what we had to do. But at the end of the day, this was possible. We managed to find the universal structure, and we managed to find a fundamental super loop equations such that it admits these loop equations of the specific model as a special example. But what we came up with was much more general. All right, so now we can define abstract super loop equations by this observation. It's highly non-trivial, but you could do it. Now, okay, good. So we have the fundamental structure underlying this story. Can we solve it? And in particular, can we solve them algebraically by super structures that I presented in the previous slide, in the previous section, and also solve geometrically by utilizing the geometry of super Riemann surface. This is what we have to do. And then, and the next slide, I'm going to show you the answer is yes. And this is how you construct the solution of abstract super loop equation. All right, so now the definition of a local superspecial curve. And this one, I really have to emphasize that this is a local superspecial curve. And we do not have a very good understanding of global superspecial curve yet. So a local superspecial curve is a quintuple that comes with a super disk and automorphism acting on it. So it just swaps a sign of Z. This is just a definition of sigma. We define this operator. And you have the choice of tau, which defines omega 01 of the topological recursion. It's exactly the same way. And you have also the choice of phi, which defines the holomorphic part of omega 02. But now, because this is supersymmetric topological recursion, you need some fermionic element. And this is basically what we have to need, what we need, in addition to the definition of the local spectral curve. So this is essentially a fermionic analog of this Bergman kernel, but in this specific form. And now let me justify why this one is a natural object to think about super topological recursion. Okay, so, yes, a few remarks about the definition of local superspecial curve. First of all, the degrees of freedom is just tau, phi, and psi. These are the only degrees of freedom that you can think of. Anything else is canonically fixed. So once you choose this tau, phi, and psi, you uniquely fixes a local superspecial curve. And now it's important point. So this big theta that I somehow define in ad hoc way, if you take a square of this capital theta, you get z dz. So you can think of the big theta as a square root of z dz, but it's a fermionic one. And this one is a very close object as, if you know the definition of super Riemann surface, it's a very close object as the super conformal structure, but it's a dual part, and it has Ramond puncture at the origin. Okay, and also if you think about this identification, when you take the limit that two of the points are very close to each other, and this fermionic version of Bergman kernel has only simple pole on the diagonal, and it's a half order differential. And this is pretty much a square root of Bergman kernel, and this is an expected form of, in terms of vertex operator algebra. Okay, so hopefully this justifies the definition of super spectral curve. And given a super spectral curve, we can now define abstract super loop equation. And I will not display what kind of form it is, but I just tell you that now you can actually find a recursive formula that solves abstract super loop equations. And that recursion constructs now omega gn/2m. So these are the bosonic insertions and you have fermionic insertion as well. But they're still like multilinear differential. They are symmetric in these variables and anti-symmetric in the fermionic variable. And we call the set of these recursion ReNewQuantum super topological recursion. Okay, so this is just a conceptual path, but now in the next slide, I will show you the formula, one of the formula for the super topological recursion. All right, so this is a part of the formula for super topological recursion. So what you want to construct is this differential. And let's do a recursion with respect to this variable Z0, so bosonic variable. And in the standard recursion, you just have the recursion kernel, and you have G minus 1 term, and also you have this product term. And you're gluing these bosonic edges, basically, in the sense of path decomposition, and it spits out this omega G n plus 1. And this is, now for the super topological recursion, you actually have to add the following terms. And you might find it little complicated, but basically these terms describe how to glue two fermionic edges. And then still you can think of path decomposition. Okay, so but this is a very natural, actually, if you look at loop equations, this is a very natural gluing in the sense of path decomposition. Okay, and then I will skip writing down the formula for this fermionic recursion, but you can write down, and you can actually find it in one of our papers. All right, so this is the definition of the construction of these differentials by this super topological recursion. And now come back to the question of Yogen. Okay, are there any relation between the super structure and this super topological recursion? All right, so as a summary, super topological recursion, again, if you fix 3 parameters, tau, phi, and psi, you uniquely fix a local superspectral curve, from which by super topological recursion, you can compute differential. And super restructure does pretty much the same job. You choose tau, phi, and psi, you take a conjugate on the differential operator, and the outcome you get is the coefficients of the free energy. So are there any relation between these two? Because both of them are recursive structure and both of them are supersymmetric. And here is the theorem about the relation. So given the choice of tau, phi, and psi, you can actually find a natural basis of expansion of these differentials. And if you expand this differential that you compute from the super topological recursion in this basis, and the coefficients are none other than the ones you can compute from the super structure. And the key for the proof is abstract superloop equation. If you have abstract superloop equations, you can show the duality between super structure and super topological recursion. And the initial data for local superspectral curve and initial data for the differential operators are exactly the same. Okay, so now let's apply this formalism to some physical questions or mathematical questions. But this is also another good point of asking questions if there's any.
I have a question.
Yep.
There's another point of view from which you might have approached the question of what is super topological recursion. You could have begun with like super Schrodinger equation and form spectral curve and ask the question, does the WKB expansion of the solutions satisfy some topological recursion? Is that true for the thing that you've set up?
So I do not have a very clear answer to that yet, but I think one way of thinking is, can we construct, so for example, starting with the topological recursion, you can construct a so-called quantum curve. It's a quantum version of spectral curve. Can we do the same story? And we expect the answer to be yes, And there's some attempts in terms of matrix models. So if you have matrix models, you actually have some global picture. And you can actually come up with like some sort of super version of Schrödinger equation. And so, yeah, so at the moment I can say there are attempts and some nice results as well, but I do not have a rigorous construction yet. So whatever example we have at the moment, they based on matrix models.
But for these examples, it's true that somehow the WKB agrees with the topological recursion.
Sorry, what's your question again?
Let me say it this way: for whatever examples you have examples with a spectral curve for which the solutions to the Schrödinger equation are in fact given by the super topological recursion.
No, I don't think we have that statement yet.
Not even in the examples for matrix models which you've computed.
For matrix models, we have a Schrödinger-like equation, and then the solution of the Schrödinger-like equation can be constructed by matrix models.
I see.
Did I answer your question?
It can be constructed by the super topological recursion.
Yes, it can be, but I haven't proven in the entire way.
I see.
Can I make just a quick comment about this question? Even in the usual case, not the super topological recursion case, it is not true that if you take a Schrödinger equation, the topological recursion will give you a WKB solution. It is true just in some very particular cases where the spectral curve for your Schrödinger equation has genus 0. But in general, it is not true. So for the super topological recursion, it will be the same.
Is it not true or not known?
It is not true.
I see. Is there some similar statement which is true, or is there just something nothing?
So there is a similar treatment. So if you wish, there will be some H-bar deformed Schrödinger equation, which will be complicated, such that the topological recursion gives you some trans-series solution in H-bar of the differential equation. If the spectral curve has genus 0, in this case, the trans-series gives you some usual WKB series, which is solution to the Schrödinger equation, which will be just mildly deformed by the H-bar.
Thanks.
So there should be the same kind of issue, I guess, for the super topological recursion case.
Yeah, thanks, Nicola. Yeah, yes. So in particular, whenever you have matrix model counterpart, normally the spatial curve is nice, and the only analytical matrix models is actually one cut. And if it's two cuts, it's going to be very complicated. And one cut model, then you expect some nice structure. But in general, it's going to be very complicated. And any other questions?
Maybe I have another question. So you didn't enter the details of the abstract loop equation. Is the statement something like some combination of your omega GNs are holomorphics?
Yes, yes, exactly, yeah.
Okay, thank you.
Yeah. So can I move on to applications? Yeah, I think I'm doing good in time. All right, so now so we have spent 45 minutes to construct two equivalent supersymmetric recursion. Let's apply one of those two, whichever convenient for you, to some nice examples in physics. But before doing so, okay, you might have wondered, okay, are there any relation between topological recursion and super topological recursion? So topological recursion, from a local point of view, is a machine that takes the choice of tau and choice of phi, or in other words, choice of expansion of omega 01 and expansion of omega 02, and it spits out symmetric differential. In super topological recursion, you have extra data and you have extra recursion. So are there any relations between differentials from the topological recursion and pure bosonic differentials from the super topological recursion? And this is the answer. So for any choice of tau, phi, and psi, in this genus 0 differential precisely matches. And however, if you go to higher genus differential, they do not match. And this is actually very easy to see because super topological recursion or super structure, whichever you prefer, it's a Pantz decomposition at the end of the day. The recursion is a Pantz decomposition, and there's no way to add fermionic degrees of freedom into the tree level. But for genus 1 or higher, you can make a loop by either bosonic edges or fermionic edges. And that contribution basically modifies some supersymmetry. So that basically is the factor why this equality does not hold anymore for higher genes. Okay, however, there exists a very interesting choice of psi and phi and psi. In particular, whenever you set both of them to 0, for all G, the differential computed by topological recursion and the differential computed by the super topological recursion of pure bosonic one, they are related by the power of 2 to the G. However, of course, if you run the super topological recursion, you get something else. You have fermionic dependence. And more interestingly, if you set these two to 0, they actually truncate at quartic order. So the only non-trivial ones are this pure bosonic one and 2 fermionic. But this is true only if you set phi and psi to 0, or a very special value of phi and psi. But this is not true in general. Okay, so now having this in mind, let's apply super topological recursion to the simplest choice of parameters. Namely, only tau 3 is 1 and everything else is 0. And then it turns out that the free energy, or equivalently omega gn / 2m, they are generating functions of correlation functions of 2,4k minimum model coupled to leaving supergravity. Okay, and then this is a natural supersymmetric generalization, because if you apply this condition to the standard topological recursion, and the physical example is exactly 2,2k plus 1 coupled to leaving gravity without super. So this makes sense. And this also justifies why this super topological recursion that I'm proposing is a natural generalization, because this super topological recursion has this example as the simplest case. But now let's look at this problem from little enumerative geometric point of view. And then if you run the topological recursion, we know very well that omega gn from the topological recursion, they are generating functions of conservative within psi class. Now, so thanks to this formula, omega gn / 0 does pretty much the same job. But super topological recursion naturally gives non-zero fermionic dependence as well. Are there any interpretation in terms of enumerative geometry? And this is an open question. We have interpretation from physics, but not from enumerative geometry. And now for the second question is for this cosine spectral curve. And 2 years ago, Stanford and Witten showed in terms of super-J gravity that if you run the standard topological recursion on this spectral curve, and then omega gn after some Laplace transform and so on, they are generating function of volumes of modular space of super Riemann surface. And I was at least I was wondering why something about super Riemann surface can be computed by the standard topological recursion. And this could give some answer to that. So for the simplest case, indeed, super topological recursion, they are very similar. However, again, the same question, are there any interpretation for this non-zero fermionic dependent differentials? Are they generating function of some other quantities? And this is an open question. Okay, so that was 2 interesting examples. And now another application you can think of super eigenvalue model, which are none other than supersymmetric analogs of the Hermitian matrix model. And this is half applications, but more like, because we got the idea of abstract super equation from these models, so of course it works. However, even though there's a surprise in the Ramon sector, so you can run the topological recursion on the Ramon sector, and then in particular look at loop equations, you can find a spectral curve, which is given in this way. And it turns out that a nice simplification between topological recursion and super topological recursion does not work anymore for the Ramon sector. All right, so now let's run the super topological recursion. And it turns out that contributions from the Airy-like branch point can be perfectly computed by the super topological recursion. However, surprise, surprise, so there's no contribution from the Bessel-like branch point when x is closer to 0 due to the supersymmetric effect. And this is a very unique effect, and I was indeed surprised when I found this. But for some reason, and okay, probably it's coming from some global nature of superspecial curve, which we don't know yet. But it turns out if you want to compute differentials of this model, you should run only Airy-like branch point, but not Bessel-like branch. Okay, so now this is the last slide for the application. Recently, by Borod, Bouchard, Steinbrenner, and Kreutzig, they proposed a very interesting relation between the following three. One of them is Nekrasov partition function and Guyotto vectors for n equal to supersymmetric gauge theory in 4 dimensions. And then by the AGT correspondence, it's been known that this is related to the so-called Whittaker vectors in conformal blocks. And then what Borod, Bouchard, Steinbrenner, and Kreutzig showed is that this Whittaker vector can be computed by topological recursion without branch covers. And equivalently, Airy structures untwisted modules of W algebra. So you may ask, can we extend this nice relation to supersymmetric case as well? And the answer is yes. So you can, so what I showed today, it's an analog of, it's a supersymmetric generalization of the topological recursion with simple ramification. And you can construct, again, you can basically do the same thing. You can even find abstract loop equations, and you can find superstructure, and you can find super topological recursion without branch cover. But of course, we don't have a global sense of superspecial curve yet. So topological recursion, super topological recursion without branch cover, it just means super topological recursion corresponding to either untwisted or mu-twisted modules of the super irreducible algebra. And then from this untwisted or mu-twisted super structures, you can construct Whittaker vectors recursively, and you can prove that it exists. And now conjecturally, this Whittaker vector is known to compute the partition function of U2 theory on C2 mod by Z2. And this is still conjectural. And so I am actually hoping that maybe this new structure of recursion helps to prove this conjecture between the 2-dimensional superconformal blocks and 4-dimensional gauge theory on the orbit. All right, yeah, so the last 5 minutes, let me just summarize it. So it's very important to just keep in mind that all the choice you have is just 3 parameters, tau, phi, and psi. If you fix them, you can either completely fix local superspecial curve or a super structure, a set of differential points. And then you can think of both of them, whichever is convenient for you, you can think of them as a machine that takes those parameters as the initial condition, and it spits out either coefficients of the free energy of the super structure or differentials that you can compute from super topological recursion. And then there are many, many open questions to be investigated. So for example, first one, the enumerative interpretations that I mentioned 3 slides ago about fermionic thing. If you choose tau and psi, phi and psi 0, and omega gn / 0 is kind of canonical, but interpretation with fermionic insertion, it's still open. And also, at the beginning of the vertex operator algebra section, I mentioned the relation between topological recursion and ramification order R and WGLR algebra. And can we extend this with supersymmetry? So can we think about super topological recursion, but now the algebra part is OSP1 to n or any other supergroup? Can we construct that? And other questions, for example, we can ask n equal 2 super-Virasoro algebra. That is a little tricky, but there's some matrix model talking about n equal 2 super-Virasoro algebra. So this is another direction that we can possibly think of. And the global super spectral curve, this actually is very important notion and coupled with probably super quantum curve as well. So how can we make sense, ideally, from some algebraic geometric point of view, how can we make sense of a local super spectral curve as an example of some supersymmetric algebraic curve? And we do not know yet. We have some hints from matrix models, but we do not know yet. And also, relating to the first question, but can we construct supersymmetric version of homological field theory? And this is something I'm now investigating with some collaborators. Okay, so yeah, I think I still have a few minutes for questions, but thank you very much for your attention. That's
okay, all. So let's thank Kento. So questions?
Hi, Kento. Yeah, I might have a naive question.
Yeah.
So, so the super array structure defines a unique partition function, is what you said.
Correct. Yeah.
So, yeah, I don't know if there are some. Seems like this is some Hamiltonian formulation of quantum field theory, and I was just wondering if you know anything about the Lagrangian that's governing this quantum field theory, maybe.
Okay, so I think this answers to your question. So, for example, the question is, how can we even come up with this set of differential equations?
Yeah, exactly. So they look like constraints on,
Yeah, exactly. Yeah, that's exactly right. So you actually, so if you, so for super case, it's a little funny because of this extra variable. It's not going to be Lagrangian. I think you can see it because, you know, the dimension is not split into two. But for bosonic case, for the standard array structures that Conservative and Soberman constructed, actually you can start from the classical algebra, then you can actually think of Lagrangian and Lagrangian complement, and then these can be thought of as quantization of that structure.
Okay. Yeah, I was thinking, like, is there some action functional, you know, behind this quantum field theory that gives you this partition function?
If I have some understanding from action function. I'm afraid if I know the answer to that question, but maybe someone in the audience, hopefully. Yeah, sorry, I'm not sure if I can answer that.
I was just wondering. Yeah.
But there could be. I could be just, you know, the knowledge less. But there definitely exists some, like the Poisson structure and the Lagrangian. Those notions exist behind this definition. That's definitely true.
Okay, thank you.
Maybe one can make some kind of Legendre transform to these Hamiltonians or something like this that could generate a Lagrange. I'm not sure.
Yeah, that sounds quite familiar.
But more questions? So maybe I can ask you, so you were saying that you expected super, you know, array structures to somehow correspond to volumes of super moduli spaces. I would say both yes and no. I mean, maybe, because you see, many instances of topological recursion, it is something not to do with curves, right? I mean, the role of that curve that we run topological recursion on is very different from what we are counting. And so, I mean, I don't see any a priori obstructions for having a purely bosonic recursion, which gives you the volumes of moduli spaces or other things that has to do with supergeometry, actually.
Yeah, that's a fair point. Yeah, that's right.
It's like also, for example, you can do. We already know that in certain cases, topological recursion gives you Gromov-Witten invariance, right? Special cases, we know this. Yet it still curves. I mean, it's still, there's no sort of, the toric variety is not, it's encoded in data on that curve, but it doesn't change from being a regular curve. And so, yeah, from that point of view, it's not surprising that one should get
of course, I totally agree with you. Yeah. I was probably just personally surprised that I was thinking, okay, maybe some supersymmetric effect should appear, but yeah, that's definitely right. The structure of the curve a priori has nothing to do with invariance you can compute.
Yeah. Okay. More questions?
Yes, I would have a question. Hi, Kento. It's a bit related to Nicolas' question. So he asked a bit more on the abstract loop equations. So you said it's like a combination of the omega g and m's is holomorphic. Is that only on the bosonic variables, or it's something on the bosonic and on the fermionic variables?
Okay, there are two types of, four. So you have two linear loop equations.
Okay.
And two quadratic ones. So linear one basically tells you the antisymmetry of the involution. And that's so for linear one, you have one for boson and one for fermion. And then for the quadratic ones, so they are quadratic differential for the bosonic ones, as you can probably imagine. And then of course, but if you have a product of fermions, it becomes bosonic and it becomes actually quadratic differential again. And now for the fermionic quadratic loop equations, they actually fermionic. So you actually have to impose that this has holomorphic, but now coupled with the big theta that I introduced. So it's kind of 3/2 differential, I think, instead of quadratic differential. But the philosophy is the same. It's still holomorphic.
Okay, thank you. And another question: do you have variational formulas in this?
Very good questions. Okay.
Or do you expect them?
I expect them to be yes. Yeah, that's definitely true. But I haven't proven it. And actually, okay, maybe I can just share with all the audience. But I haven't defined a free energy.
I see. This was part of the.
But this was possible. I've already checked it. So the inverse of loop insertion is possible. So you can have the primitive YTX and you can act on it and then you can actually cook up something. So the definition of the free energy makes sense in a standard way.
So you have a dilaton equation.
Yes, but I haven't written it. So
okay.
That's what I meant by But the variational formula, yes, I do expect that. In particular, because we have matrix models. So okay, the original proof is given by the graph decomposition and so on, but I expect that to be, so the answer, I think expect that to be yes, but I haven't proven it.
Okay.
But that's actually a very important direction.
Yes. Okay. Yeah. Thank you.
Yeah, thanks for asking that.
Any more questions? No? Well, then maybe let's thank Kento again. Okay.
Oh, yeah. Thanks so much.
Thank you. Okay. And yeah. Thanks a lot for the talk and thanks to everybody.
Yeah, thanks so much, everyone, for coming.
Okay. Yeah. Thank you for a good talk.